Hello everyone, this is Vishnu and concept video topic for theory of computations is on introduction to deterministic context-free language. So let's get started. So what exactly is a language first? So a language is a set of strings from some alphabet, finite or infinite. In other words, any subset L of E star is a language in theory of computations. Some special languages are as follows with the empty set or language containing no strings, or S, a language containing one string, the empty string. So these strings would form up to be a language for the machine to run on. So these are the commands which are sent to the computer back in the days with the help of tapes, paper tapes, so on and so forth. And on those tapes, it's nothing but the strings which are there uh, that machine understands and does the processing. So, what is context free language? So, CFG stands for context free language. It is a formal grammar which is used to generate all possible patterns of strings in a given formal language. It's all possible patterns in the sense if we have anything like a string which would be like a which is a b to the power of n, then the possible strings would be a b b, a b, a b b b if n is 3, and a b b b b which when n is equals to 4, and so on and so forth. Those are nothing but the all the possible patterns of strings in a given formal language. Sorry. Context-free grammar G can be defined by four tuple notations as V, T, P, and S. So where V is nothing but the final set of non-terminal symbol, T is the final set of terminal symbol. Terminal in the sense uh, it stops. So let's consider where n equals to greater than 0 and n is less than 3, let's say. So it would be a b to the power n, then a b, a b b, a b b b, and the string term. I mean the possible number of patterns. Well, those are the possible number of patterns, and the string got terminated, or the language has been terminated. Where it comes to non-terminal symbols, they keep on repeating. So that's what it basically means. And P stands for a set of production rules used for replacing non-terminal symbols. So if there are any non-terminal symbols, then these symbols will be replaced with something else, so that so as to terminate the process. So S is nothing but the start symbol, which is used to derive the string or state that this is the start of the instructions, or this is the start of the language, something like that. Moving on, deterministic push-down automata, DPA. In automata theory, deterministic push-down automation, DPDA or DPA, is a variation of the push-down automation. So the class of deterministic push-down automata accepts the deterministic context-free language, a proper subset of context-free languages. So A not necessarily in deterministic, so PDA, basically push-down automata, can be defined as a seven tuple notation which consists of Q, epsilon, uh, not sure, and Q naught, Z naught, A, and delta. So Q is a finite set of states, um, which somewhat looks like epsilon is a finite set of input symbols, uh, is a finite set of stack symbols. Q naught belongs to Q, is the start state. Z naught belongs to is the starting stack symbol. Uh, A Q, where A is set of accepting states, and delta is a transition function where delta stands for Q times epsilon union set of epsilon times symbol which tends which which leads to P of Q times symbol times R to the star. So M is deterministic if it satisfies both following conditions. So for any Q belongs to finite set of states, then A belongs to epsilon union set of epsilon comma X belongs to the symbol, and the set of delta of QAX has at most one element. Delta is nothing but the transition function, and the second condition would be the for any Q belongs to Q, X belongs to the symbol if delta of Q epsilon comma X is not equals to the final state or null state, not final state, it's the null, then delta of QAX is equals to null for every A belongs to the epsilon. So there are two possible acceptance criterias. I will acceptance by empty stack and acceptance by final state. So MC and the two are not equivalent for the deterministic push-down automation. And so here comes the deterministic context-free language. Uh, the L can be a language defined over the alphabet. The language L is deterministic context-free if and only if it accepted by the deterministic push-down automation. So not all context-free languages are deterministic context-free. Are deterministic context-free, and L1 equals to WCW to the power of R, where W to the power R in the sense if we consider W as A or AAB, then W to the power would be BAA, which would be the complete mirror of the initial string or the string sequence of letters. So W to the power of R would invert the sequence of the strings. So L1 is equals to WCW to the power of R, where W is a set of A comma B to the star, is deterministic context free, and L2 equals to WW to the power of R, where W equals to the set of A comma B star. Here star would represent that there could be any n number of uh, letters possible. Like if we consider a if we consider both A B, then we cannot consider both A B or we can. So A or A can be there can be any number of A's, and at the same time there can be any number of B's, and both the sequence any number of A's plus any number of B's. So that's what the star would represent. So in the L2 case, WWR is context free but not deterministic context free. So these L1 would lead us to uh, the one of the states of acceptance, which is nothing but the first state, the empty stack. It would be accepted as the empty stack because uh, for W we'll be pushing all the elements into the stack, and in the same order, since it's reversed, we can pop the elements are since the elements are reversed, it's easy to pop the elements which are there. because they are arranged in a way that it can be done. If it's A, B, so in top of the stack it's B, and the next letter after C is B, and since top of the stack it's B, so this B and that B would cancel out each other, and cancel out each other in the sense we are allowed to pop the top element of the stack, and similarly then A and then A, and that's how we would reach to an empty stack, where empty stack in the sense is not completely empty, but the initial value, which is nothing but z naught, would remain intact. So when z naught is there at the top of the stack, then it is the time, or we can say that we have reached the empty stack. So this all for a deterministic context free language. Thank you.